Hey, what is up everyone? I hope all of you are doing great, and in today's question we have two identical uniform disks, each of mass m and radius r, are placed on a horizontal frictionless flow. One of the disks is given an angular velocity omega about its stationary vertical central axis, and the other is projected with a horizontal velocity u without rotation for a head-on collision to occur between them. Fine. If the collision is perfectly inelastic and slipping between the disks ceases, okay, so the relative slipping is 0. In the end of the collision, find angular velocities of the disk and speeds of their centers after the collision. Okay, so let us go through the solution. So initially, the first disk was rotating with an angular velocity omega with a stationary axis. The axis is not fixed, but it is stationary. Uh, with an angular velocity omega, I have considered it in the clockwise direction, and the second disk is coming towards the first one with a constant speed u. Of course, it is not rotating. Both the disks suffers a head-on collision, and the collision is perfectly inelastic. It has been mentioned in the question. Okay, now just after the collision, the second disk will be just touching the first one, but I have separated these two disks so that I can draw the impulsive forces and velocities properly. But remember that these two are very close to each other. Okay, so these 2 points are nearly in contact. Now, as collision is perfectly inelastic, so velocity component along the line of impact will be equal after the collision. So conserving momentum along this line, we get v1x, which will be equal to v2x, and it will be equal to u by 2, right? So this one was pretty easy. For coming to our final solution, we need to find out more 4 unknown variables. Okay, omega 1, omega 2, v1y and v2y. So we need 4 equations. So let us see. Second equation we will obtain by conserving angular momentum with respect to the axis passing through the center of the first disk. Okay, so conserving angular momentum with respect to this axis. So initially it is I times omega, that is mr square by 2 into omega, and this one will have 0 angular momentum because it is not rotating at all, and the velocity component is passing through the axis itself. For this, after the collision, according to my diagram, the angular momentum of this disk would be mr square by 2 times omega 1. Angular momentum of this one with respect to this axis will be equal to angular momentum of the disk with respect to center of mass, that is I times omega 2, plus angular momentum of the center of mass with respect to this axis, that is m 2r, as I have already said that these two are very close to each other. So 2r times v2y, that is the perpendicular component of the velocity, right? So solving this whole equation, we get this one in the reduced form. So for the first disk, okay, and now of course there is an impulsive force acting on the first disk just during the collision, and due to that impulsive force there will be a change in momentum. I have considered the impulsive force or the impulse along the tangent only. Of course there is an impulse in the normal direction, but that is of no use for us. So due to this impulse there will be an increase in momentum, that is m times v1y. This impulsive force is also creating an angular impulse. So anti-clockwise direction, I have taken a negative symbol, clockwise direction is positive one. So angular impulse with respect to center of mass is minus jr, creating a change in angular momentum, that is I times final angular velocity minus initial angular velocity. Okay, reducing it to v1y. So this is our second equation. Okay, for the second disk, right, for the second disk initial situation was this one, and of course on the second disk the impulse will be acting on the opposite direction. So here the impulse is changing the linear momentum in the vertical direction, that is m times v2y. This will also create an angular impulse, that is minus jr, anticlockwise direction, which is equal to change in angular momentum, that is I into omega 2, right? Solving we get v2y equals minus omega 2 r by 2. Fine. Now in our question they have already mentioned that just after the collision the slipping between the two disks becomes 0. There is no slipping, right? That means the velocities of these two contact points will be same after the collision. So velocity of A will be equal to velocity of B. I have taken the vertically upwards direction as the positive direction. So velocity of point A would be v1y, velocity of center of mass with respect to center of mass, and velocity of center of mass. So this will be the velocity of point A will be the vector summation of omega 1 r and v1y. So v1y minus omega 1 r. Similarly for point B it would be omega 2 r minus v2y. Okay, solving it 2 and 3. So using 2 and 3, that means what is 2? 3 is v2y and 2 is v1y. So using these two values, and I am plugging it here, simplifying it, we get 3 omega 1 plus 3 omega 2 equals omega. Okay, there are a lot of equations. Don't get confused. Just after my solution, try it at your own speed, at your own comfort. Okay, so we got our fourth equation. Now putting the values of v2y in 1. So we already have v2y, and we'll just plug it into equation 1. So what do we get? Okay, so we got omega equals to omega 1 minus omega 2. Okay, so we have two equations from where we can find out omega 1 and omega 2. So the fifth equation, and here is the fourth one, this fourth equation. So just solve these two equations. You will get omega 1 as 2 by 3 omega and omega 2 as negative omega by 3. That means just after the collision, the second disk will start rotating in the opposite direction of our predefined direction, right? So we have considered it will rotate in the clockwise direction, but after collision it will rotate in the anti-clockwise direction. So negative symbol symbolizes that result. Okay, so two angular velocities we have already got. Now here comes the value of speed of the center of mass. v1x we have already got as u by 2. v1y, that was our, I think, first equation or second equation, I don't know. Just put the value of omega 1 here and you will get omega r by 6. Similarly for 2, v2x is u by 2, v2y will be omega 2 r by 2. There was a negative sign, but I am taking the magnitude only. So just put the value of omega 2, omega r by 6. So speed for the center of mass of first disk is this one. I know I have listen, I have not told you how to solve this simultaneous equation. Of course these are very simple for you people. I've just shown you how to create equations, because for JEE Advanced the most important thing is to know how to create equations. Okay, now of course I don't need to tell you how to solve them, because you people are smart enough to solve equations, but you first need to know how to create equations, like how to use conservation laws in the situations. Okay, those things are more important. I might come with a different series where I'll be telling you how to use conservation laws and how to create equations in advanced questions or difficult situations. Okay, especially in this rotational mechanics creates a lot of problem while creating equations, because choosing the axis and a reference point and many things are there. Okay, so I hope you all have found this video helpful and informative, and if you are new to this channel, please subscribe and let us make our family till 1000 subscribers as soon as possible. And if you like the video, give a thumbs up. I'll see you in the next one. Peace.